Okay, so in the last video you saw how practical sources they could be transformed into an equivalent voltage or current source or vice versa, whichever way you want it to transform. So let's just use those phenomena to basically see how circuit analysis can be used using those, right? So when I see the circuit, I know I need to find Ix, that's the question. So the two things I note is that this is a practical source because there is a resistance in series with the voltage source, and this is also a practical source because there is a resistance in parallel to the current source. So which one to transform? I can transform either one of these and it would not have any effect on the answer. But something, using common sense, I can see that I need to find this current. And if I just transform this source, this current, it would just go because it would come in series with the current, with the voltage source. So I'll just start off from this side and I'll transform this voltage source. So let's just see what's the use of that. So we know that this stays the same and this value would become 5 because V is equal to IR. So 5 divided by 5 kilo ohms, that would be 1 milliamp, because that's 5,000 ohms. So 1 milliamp, and then the rest of the circuit it would stay the same. And then there is the 1 milliamp source. So this is my circuit and I need to find this Ix. So one thing I can clearly do is that these two current sources, they are in parallel, so I can just add them up. So I'll just add them up, that will become 2 milliamps, and I'll just draw the new circuit in the next slide. So now after combining those two current sources, I get this result and I need to find Ix. So now I can clearly see that this is a perfect circuit to apply the KCL, the CDR, the current division rule. So I'll just apply the CDR and Ix would be 3, the total current to the parallel combination, times 5 divided by 5 plus 47, and this would give me Ix, where the answer would be 192 microamps. So as you saw how transforming the one voltage source here, that really helped me, to solve the entire circuit and to bring it into a form so I could apply CDR. So this is why sometimes this source transformation phenomenon is very useful. So now let's just see another example. Alright, so in this circuit, I need to find IL, which is the current going through this branch. So as I can clearly see, I can use a source transformation for this source because there is resistance in series, and I can also use a source transformation for this source because there is a resistance parallel to the current source. So I'll just start off from this side because I need to find this current IL, and if I use source transformation on this source, this resistance would will go in parallel, and that would just change the entire circuit. So I'll just use source transformation here. So using source transformation, I can clearly see that the internal resistance that would stay the same. There would be a 4.7 kilo ohm resistor, and then would be a 3 kilo ohm resistor here, and then there would be a 3 volt source. And now what would be the value of this voltage source? Well, I can find it using V equal IR. The current is 9 milliamps, so 9 divided by 1000 into the resistance, which is 5 kilo ohms, 5 times 1000, and that means the voltage would be 45 volts. So now I have this voltage, I have this voltage, I need to find this current. So I can just use KVL and I can find the current. So I won't go into the calculation, but this also gives you an idea why source transformation, they are really helpful in solving sub circuits, especially because they allow you to bring the circuit from a series form to a parallel form, and form those combinations where you can apply the CDR or the VDR. So I hope you understand, you got the idea.